great pleasure to invite Alwyn Seeds, G8DOH, to talk about coax and connectors, the forgotten ingredients. Take it away, Alwyn.
How about that? That sounds more like it. Right. So this talk is about things that actually make the most huge difference to how well things work, but yet they don't get a lot of attention. So talk is about coax and connectors. We all use coax cable, and we're all highly interested in, the latest gadget that we attach to the end of it. But actually, what we do with the feeder actually probably makes more difference than a lot of the hardware we attach to the end of it. So I'm going to talk first about system needs, and there are little equations in this, but they're fairly simple equations, and the conclusions can be expressed in words, so there's no need to worry particularly about them. Then I want to say a little bit about what actually affects coax cable performance. And most of you probably have learnt this, possibly many years ago, but I think it's worth reminding ourselves of the principles by which it works, and therefore what's important in having good coaxial cable. Then, in turn, I'll talk about choosing cables, choosing connectors, which is if I were giving this talk 20 years ago, choosing connectors would not be a difficult problem. These days, it's a really huge problem, so a little bit about choosing connectors, and then finally conclusion. So it's the standard revision slide. Since we'll be talking a lot about decibels and powers, decibels are 10 log to the 10 of a power ratio, and powers are decibels relative to some reference power, a milliwatt, or in this case, mainly a kilowatt. So here's my VHF UHF system. It's a nice simple system. It has a transmitter and a receiver. The transmitter has an output power of P0, and the receiver has a noise factor of F. And as a result of that, there will be some transmitted power going out of the aerial, and there will be an equivalent receive noise power. Those numbers, of course, are not the same as numbers that apply at this end of the system. And in between is the feeder, which has loss factor L. If the feeder is lossless, L is equal to 1. If the feeder has a loss of, loses half the power, then L will equal 2. It's a numerical, it's not a dB number in the equations. So that's what we need to do. That's the system we'll be working with throughout the talk. Let's talk about transmit, because transmit is actually the simplest part of the problem. We put out some power from our power amplifier, whatever it may be. It goes through the feeder and comes out of the antenna. The ratio of the output power of the transmitter to what comes out of the antenna is the loss of the feeder. So if you have half a dB of feeder loss, the loss numerically is 1.12, and to get 400 watts at the antenna, you need 450 watts. And as you go up in feeder loss, you need more power. So if you have 2 dBs of feeder loss, you need 630 watts coming out of your PA. Now, it's a simple observation, but power costs money. And in round terms, once you get above some tens of watts, you have to get over the threshold of having something that will transmit. And then when you want extra watts, you pay. And you pay roughly at VHF, UHF, you pay about £1 a watt. Some of your home-built watts will cost you less than £1 per watt. Some certain commercial watts will cost you more than £1 a watt. But it's about that level. And the point, therefore, is that here I have 233 watts I'm disposing of. I'm also destroying the planet and ourselves and doing all those bad things. So you can buy yourself a reasonable feeder for £233. It's worth thinking about that. Just do the economics. Good feeders save a lot of money. And that's it for transmit. You need feeder that will stand the power, and you need feeder that will give you low enough loss. Those are really the main problems you wrestle with. On receive, it's much, much more complicated, because what you need to worry about is the equivalent noise at the input to your system. If you work on EME, particularly at the microwave frequencies, you're going to have to reduce that to the minimum possible, and that needs a lot of care. If you're dealing with the terrestrial, as we will see, you don't have to be quite so careful. But you have to get that number right, otherwise you miss signals. And that power is given by Boltzmann's constant times the system noise temperature times the bandwidth. We normalize everything in this to a 1 Hertz bandwidth, and so you can just multiply by whatever bandwidth your receiver happens to be receiving in. So we said we had a received noise factor of, at the receiver, of F, and therefore the receiver has a associated noise temperature, which is just calculated by moving that formula around. And for the purposes of my example, I'll deal with a moderate receiver. It has a noise figure, that's the log version of noise factor, of 2 dB, or a noise temperature of 168 Kelvin. Now, you might say at first, well, my transverter's way, way better than that, but that's not actually the noise figure of your receiver, because you've got a tunable IF after it, which is usually an HF radio with a really rotten noise figure, and therefore the sort of average kind of transverter and HF radio setup usually ends up somewhere around there, not much better. So that's going to be my starting point, but we have feeder in the way, in between the receiver and the antenna, and so we have a system noise temperature here, and that system noise temperature has two components. One, the aerial noise temperature, which is all the noise that the aerial gets, and the other bit is the referred part of the receiver noise temperature. So I call that received system noise temperature. So we need to know how to calculate TR and what effect does the feeder loss have on it. The reason I'm going through this is because how many of you have masthead preamplifiers? See? The majority, no, less than the majority, but a lot. How many of you have masthead preamplifiers on 6 meters? Only a few. Well, that shows that here is a case where democratic arrangements work correctly, because most of you have made the right decision, depending on what you're going to do with your system. I'll just give you that exception.
We'll think about what I do with my system.
Yeah. So, what will the system noise temperature actually end up being? If you have, let's check it out. If you have a lossless feeder, L is equal to 1, and lo and behold, when you plug that into this formula to refer the received noise temperature up to the antenna, you find if you've got a lossless feeder, you simply get the noise temperature of your receiver. No effect. So that's great. Lossless feeders are very good on receive. However, now let's put a bit of feeder loss in. We'll assume that the feeder loss is a couple of dBs for the sake of this discussion. Then, with a 2 dB noise figure receiver, what was a noise temperature of 168 Kelvin, which was the value at the receiver, at the antenna becomes 433 Kelvin. And that is happening for two reasons. One, the feeder that you've connected has some loss, so you lose power, but also because I've assumed that the feeder is sitting at a temperature of sort of roomish temperature, 290 K, and therefore being a lossy element, it generates some more noise and makes the performance worse. Interestingly, my colleagues who do quantum type experiments, and they all work at suitably low temperatures, their equation of course looks different because their feeders taking the microwave signals into and out of the experiment are all at liquid helium temperature or below. So they don't add much of that noise there. The only one you have to worry about is the loss-related noise. And if you are doing quantum manipulation of, rather tiny ensembles of electrons, you find you are a bit worried about noise. Anyhow, in my experiment, my receive system noise has more than doubled, and the question is, does it matter? The other factor in my system noise is the antenna noise. And at 6 meters, the minimum you can get is Galactic. Not many people actually get 2000 K looking at the horizon, even in the quietest directions. 4 meters is a bit quieter, it's gone down to 800. 2 meters is 300, 70 sems considerably quieter, 180, 23 sems about 150. That's just looking at the horizon, minimum noise direction. And there's nothing you can do about that. That's what's going to be there. If you live in the real world and you have any neighbors, solar farms or anything else, your aerial noise will be much worse. In London, it's so bad that there's no point in doing VHF amateur radio. So these are about the best figures you're going to get. So remember that the sensitivity is going to be set by the system temperature. You've got this to add in whatever you put there in the way of receivers. So this graph shows the penalty that you get as a function of feeder loss on different bands, 6 meters, 4 meters, 2 meters, 70 and 23 centimeters. So 6 meters is up here, and when I go from a feeder loss of no dB to 3 dB, I shift my system noise floor by about a dB. It's almost nothing for practical terrestrial communicating. It, of course, gets worse on 4 meters because the aerial noise contribution is smaller. So feeder loss matters a bit more, but not all that much. 2 meters is beginning to get to be the turning point because in my example, things have got 2 dBs worse with a couple of dBs of feeder loss, which is not great. And when I go to 70 and 23, it's even worse. So it's a basic point. If you don't have much received noise on the aerial, then it really matters how low your feeder loss is. And so when feeder loss tends to need to be impractically small, you solve the problem by having to have a preamp right at the aerial. But except for special reasons which John will explain to you, except for those special reasons, if I'm just trying to have some standard sort of 6-meter QSOs, I could almost use wet string for the feeder and, you know, I'd be quite happy. So you don't always need masthead preamps, is the message from this. And what I would say overall for feeders is that transmit power loss tends to be the thing on the lower frequency bands, and I really don't think having more than 2 dBs of feeder loss is a good idea on economic grounds. You're going to have to work harder at 70 centimetres, and it becomes a marginal thing as to whether you might benefit from a preamplifier on that band, depending how you can engineer your feeder. 23 SEMS, you pretty well certainly have to do this for a high-performance station. And finally, the caveats. If you add a preamp, you will, of course, reduce the strong signal handling capabilities of your system, and that might be a worse, in fact, if you're building contest stations, is likely to be a much worse problem than a very small improvement in receive sensitivity. Right, so we know what we need now. We need feeders certainly with less noise, with loss less than a couple of dBs, and now we've got the problem of getting that. So a revision on coaxial cable. It's been around since Heaviside, which is an awfully long time, and what it comprises is an outer conductor and an inner conductor. The outer conductor diameter is D, the inner conductor diameter is little d. And the characteristic impedance of the stuff is given by numerical factor, 138, divided by the square root of the dielectric constant of the dielectric you put in between those two, times log to the base 10 of the outer diameter divided by the inner diameter. Now that equation is incredibly important because we work in the systems we build generally at 50 ohm characteristic impedance. So this number is fixed. We can modify D and D, and we can modify epsilon r. Those are the things we can play with. And so the question is, what should we do? Coaxial feeder loses signal, i.e. it creates loss, feeder loss, for 3 basic reasons. First of all, radiation loss, leakage of the signal through gaps in the outer conductor. In the 1960s, when copper was expensive, a coaxial cable was devised for UHF TV purposes, which used to be known as bikini braiding, because there was so little copper in the outer. Cables like that lose signal by radiation loss really rather badly. Secondly, there's dielectric loss. If we do include a dielectric, then it has loss tangent. However, if that dielectric is good quality, polyethylene or polytetrafluoroethylene, the contribution to feeder loss from it is essentially negligible up to 23 centimeters. It begins to come in at the microwave frequencies, but this is a VHF, UHF talk, not a microwave talk. And third, and this is a big one, conductor loss. Just the resistive loss in the materials we make the conducting parts of the cable from. So we've got to minimize these somehow. There's something that makes the job really difficult, which I want to emphasize, which is skin effect. It is hard to launch an electromagnetic field into a conducting medium, like the cable inner or the cable outer. Because of that, most of the current at high frequencies flows in a thin layer close to the surface of the outer conductor and the inner conductor. That is totally different from the situation with a low frequency or direct current cable, where the current is spread out over anything that can conduct the current. So you measure the DC resistance of a bit of coax and it's almost nothing. But it's a very, very different story when you go to high frequencies, and if you have connectors with little pins that fit together and so on and so forth, and you think, well, that pin doesn't look that small, I'm only putting 400 watts through it, should be fine. Don't forget, you're not putting 400 watts through the pin, you're putting 400 watts through a rather thin little layer of the pin. And the thickness of that layer is given by this equation. It's quite an interesting equation because it's determined by the resistivity, the frequency, and the permeability. And we'll see why this is so important in a moment. So the basics first. The skin depth is the thickness where the current has decreased to 1 upon E, that is to 37% of its value at the surface. So from this equation you can see the higher the frequency, the smaller this value of skin depth will be. It's inversely proportional to the square root of the frequency. Secondly, the skin depth is proportional to square root of the conductivity, so the more conductive you make something, the thicker will be its skin depth. And this one is rather important, the permeability. Inversely proportional to the permeability. If you have your conductor is in any way a magnetic material, that may have a profound effect on the skin depth, and we'll see the effect in just a moment. By the way, I write for enthusiastic physicists in the room, of which I'm sure there'll be quite a lot. Notice the update. The vacuum permeability is now approximately 4 pi times 10 to the minus 7 henries per meter. That is because we have redefined the amp. And now this is a measurable constant. It's not part of the unit system anymore. And I think the change it makes is about 1 part. It's about 1 part in 10 to the 5th. It's not totally negligible. So now mu naught is approximately 4 pi times 10 to the minus 7. It's a huge change to the SI unit system. Right, so practical things. Calculate the numbers. Here are some materials, and here are their skin depths. So these are things that are worth remembering. This is worked out at 2 meters. So at 2 meters in gold, the skin depth is just 6 microns, 6 millionths of a meter. All the current has to go through that layer, essentially. Now your resistances are going up and your losses are going up. Silver's a little better. Copper's better still, but doesn't tend to do too well when it tarnishes. Aluminium's pretty good too. Obviously, if that oxidizes, you won't get any current flowing through, for example, a connector. Believe it or not, there are coax connectors made out of aluminium. Some very interesting wartime products, Second World wartime products of that nature. But watch out for nickel. Nickel is a magnetic material, and because nickel is magnetic, its conductivity isn't bad, but its mu r is huge. Because of that, its skin depth has gone down to 0.4 microns. Now, if you try and put RF current through something that is nickel plated, you will struggle. And worse still, because it's magnetic. You remember doing physics and plotting hysteresis loops for magnetic things, and the field went up and you tried to plot the thing. They were great experiments because you put current through things and could melt them with a bit of luck. That hysteresis loop applies if you start trying to stick RF currents through it. and it creates the most horrible intermodulation distortion. So nickel is something you do not want near things that carry RF. Mild steel has the same problem. Stainless steel, you can get stainless steel in forms that are not magnetic, and that's great, but you can also get stainless steels that are magnetic, so I often take this with me in my travels. It's just a little fridge magnet, and so you can take somebody's nice product and you can just see if it's magnetic. And if it's magnetic, you don't want it. Of course, it may have plating to remedy the thing, but at least as a first order, it's a pretty simple test, and so might as well do it. Then, if you think things are bad at 2 meters, go up to 23 centimeters, where this is for copper, where the skin depth's down well under 2 microns. It's a very, very thin layer. That means the plating quality of things has to be superb, because if they're not very well plated, so the surface is rough, the actual resistance value will be way above the bulk resistance of the material. So people who are not very good at making connectors and don't have very good plating lines, they will have performance in their connectors way worse than you would expect from this. So now, on to resistance at VHF, UHF. You work it out the same way as at DC, but you've got the resistivity, the length of the conductor, the size of it. So in this case, if we're going through the skin effect depth on the outer, it's pi times the big diameter times the skin depth, and on the inner, it's pi times the little diameter times the skin depth. So the point is very simple. Because the inner in a coaxial cable is smaller than the outer, most of the loss is in the inner of the cable. And in order to minimize that loss, you need to make this little d as big as you can. The limiting factor as to how big little d can go is that if you make the cable huge enough, like a meter diameter or something like that, you'll be able to excite waveguide modes in it, and then it will propagate signals in a very strange way. So in my days of being involved with big radars that enabled you to look at things a long way away, when we were doing 70 centimeters, we found that the best way to move the powers we needed to move was just to use waveguide. It was very big waveguide, but it could take an awful lot of power. So, with that in mind, look at the equation for the characteristic impedance of the cable and its resistance. So we need to make little d as big as we can for a given size of cable, which is big D. So we can do that by making epsilon r as small as possible. So if epsilon r is air or vacuum, that will give us the largest size of little d and the lowest loss. So we like to have big cables, and we like to have low dielectric constants. So the original Heliax cables, which had air dielectric and still used for large broadcast cables, that's the way to get the lowest loss. Oops. Now on to the practicalities. This was, as I said, when Coax wasn't a mass market, this wasn't so difficult. It's now quite difficult because it's a mass market. There are some standards to which you can try to buy cables. The old one of the sort of UK-based uniradio cables to Defence Standard 6112 Part 9, the people who still work in that area can advise me of the latest, but Part 9 seems to be in some degree of uncertainty because the old BS British Standard 2316, which is referenced all over the place in it, has been discontinued. So I'm not personally 100% positive that a cable I buy which is labelled URM something or other is still bound to standards, but I would await advice on that. The situation with the US MIL standards is okay because that's still in force, MIL DTL 17. And if you buy cables from an approved supplier that meets that, and you will find the cable is marked in a particular way, which I'll show you later, then it should meet what's in the specification. Next thing down on the list are what I call professional cables, which are made by manufacturers such as these, who make them to a closely defined standard, and they're fine. Then there's other. Most amateurs insist on buying cables called other. And I'll tell you a bit more about other later in the talk, but I worry about other. I also worry about the fact that it's actually cheaper to buy the professional cables than it is to buy other. So I find this behavior particularly inexplicable. So starting with cables which have polyethylene dielectrics, there are some standard ones like URM 76, that's the thin stuff, or its MIL near equivalent M17/28, which we used to call RG58, but watch out, because all RG numbers as such, if you just get a cable that says it's RG something, it has no meaning anymore, because that standard is discontinued. So anything can be called RG213, anything can be called RG58, and frequently is. If, however, it is M17/28-RG058, and it has the right supplier on it, it might actually meet the specification. So these aren't going to be any good for our feeders, because for 30 meters of the stuff, even at 100 megahertz, the losses are far too high. URM 67, which is much the same as M17/74, RG213, might just about do it, certainly for portables and short bits of coax. That's quite useful. If you actually look at coax in detail, though, watch out for things like the humble M17/28 RG58 isn't actually rated to be used above a frequency of 1 gigahertz. This is a plot of its transmission loss up to 3 gigahertz. You see it behaves quite nicely. But what doesn't look as pretty is this, which is the return loss from the cable. The cable, actually, from being about minus 40 dB return loss at low VHF frequencies, this is not a bad, this is a mil-spec piece of cable. It's about minus 25 return loss up, and with a little glitch in there, going up to 3 gigahertz. So do be careful if you use cables outside their rated frequency ranges. Then, how about, oh yes, and this is the first of my hand-arounds. How about aging? This plot shows, first of all, the black curve is the specified performance of URM 67. That's this stuff. And it's down there. Then the other curves are a 2012 piece of this stuff taken off reel, which you see actually meets its spec. It's better than its spec at 1 gigahertz. So that's good. However, these two are RG213, which should be equivalent. One comes off a tower where it was from 1997 to 2005. Look at the loss. It's essentially, it's gone from 2.5 dB to 3.5 dB at 1 gigahertz. And here's a bit of it. I'll hand it over and hand it round, everybody inspect it. Gradually, water gets through the braid. Gradually, the PVC, under the influence of sunlight, starts to, what should I say, emit plastic things that make the braid more resistive than it should be, and the loss goes up. So the message is a simple one. And this one is a very old piece of RG213 that we had in the lab. It's been sitting in the lab since 1977. So it's had an extra 20 years, and it's up at this sort of loss as well, in a pretty well benign environment, just sitting in, you know, room temperature without any sunlight damage. So the message is that braided coaxial cable is not forever. You should test it from time to time, and if it's gone lossy, replace it. If you need more power in a given size of cable, then change the dielectric to PTFE, because that will stand a much higher temperature before it softens. So these are PTFE dielectric cables. Again, I hand round examples. It will take quite a long time to go around the room with these. That's little RG316, which is PTFE insulated. Quite a useful cable. I mean, it's no use as a feeder, as you can see from its loss, but its power rating is remarkable. You can put 110 watts through it at a gigahertz through that little cable. I have actually tested to ensure that you can do that. I've done that experiment. You can. It gets quite warm. That is for warming the cable up to just under 200 centigrade, so don't touch it. But it will take that power. If you need a bit more, so if you're building PAs, you'll find this stuff, which is RG400. I'll hand this to someone else so it can do the rounds in an opposite direction. That's RG400, which is like an RG58, but made with PTFE. The jacket is fluorinated ethylene polymer. Believe it or not, that will take 600 watts at a gigahertz. And it will. I don't recommend it, but for sort of building a couple of 100-watt, 23-cent PAs, it's acceptable. And then if you get more extravagant, if you just want a strong cable, RG142 has a plated steel core, and it's very nice for military usage because the squaddies can pull at it as hard as they want, and they won't succeed in elongating it unless you have several of them and they're fit. So it's a nice tough cable, much loved for building military things with. And then if you want to be really nasty, try a bit. I'll throw this carefully because it's heavy. That is glorious M17127 RG393, which is a big version. It costs a lot. It'll take over 1.3 kilowatts at a gigahertz. It's a nice jumper cable, that. Onward, though, we said we need low epsilon R to get a good result, you know, to actually get lower loss at a given size of cable. So this is a rather nice cable. This is times LMR 400 Ultraflex. It's about the same size as RG213, but it has a foamed polyethylene dielectric. It's starting to meet our loss criteria. Even 30 meters is 1.5 dB. And note some things about it, particularly when I hand it round. Look at the braid coverage. It is almost, you cannot see in any way through the braid on this cable. It has foil underneath, but even if the foil cracks, it doesn't make much difference because the braid coverage is excellent. Also, they've got enough sense, the manufacturers of this cable, that it's a tinned copper braid and it sits on aluminium. Believe it or not, there are some cables sold to amateurs that have copper braid on top of aluminium foil in a coax cable. Well, you know something about electric potentials and things and damp and what will happen, but it won't be nice. So that's Ultraflex, makes nice rotator loops. Who should we throw this to next? Let's try in the extreme range. Bingo. So that's quite useful stuff, and it has a bigger brother, LMR 600 Ultraflex, 15 millimeters diameter. These will take legal limit sort of powers at 40 degrees centigrade, so they're useful. Once you've exhausted those to do rotator loops and similar, you need something for the main feeder. And that's when we get to these wonderful cables that have been around many, many years and are really, really useful. Things like Cellflex, LDF 450, well-known Comscope product, and the others, where instead of braid, there is a basically it's a corrugated copper outer. So it's not very flexible. You can bend it to big radii, but for a main feeder, it's superb because it has a low dielectric constant foamed dielectric, and that enables it to have a nice big conductor. I've got 5 minutes and I've got to get through connectors. So hand that one round. We are going up in size of connector. And then this, which is even nicer, this is 7/8 Heliax LCF 7850, which is just bigger and has lower loss. And look at the beauty of this, because at 100 megs, 30 meters of this gives you 0.35 dB of loss. So on my system, because I have to get a rigger to go and climb the tower if a preamp goes wrong, I like using this stuff because I can work without preamps on most bands. So this is great stuff to use. Over to you. So that's my amateur coaxes. There are larger coaxes available. But here are the purchasing points. Watch out for weasel words. You will see a lot of specifications that say based on, equivalent to. There are many types of LMR 400. Actual LMR 400 times microwave is a registered trademark, but they are equivalent to. Well, maybe they are, maybe they're not. RG213 type. Yeah, okay. So those be careful of. Be careful of things that just call themselves RG something or other, because those specifications haven't been around since the 1970s. So anybody can call anything RGNNN. Look for the specified labeling if you are trying to buy something to mil-spec. Most of the cable, these numbers have changed because the military requires things that don't create awfully poisonous things when they catch fire. And for braided cables, make sure that you've got at least 92% braid coverage, otherwise you're just going to be radiating signal all over the place, which is no good. So finally to connectors, and it'll have to be in brief. PL259 and SO239, if you do them up tightly, they're not constant impedance, but they do work up to 500 megahertz, and you can put 1.5 kilowatts through one at 500 megahertz. Just make sure it's tight. If it's even slightly untight, horrible things will happen. But it's excessively malign, this connector, other than the tightness problem. The little BNC is rated for use up to 4 gigahertz. And notice that these are the manufacturer's power ratings. It's rated for 1200 watts at a gigahertz. The N-type, the standard one that goes up like this, that goes up to 11 gigahertz. This adapter certainly will not go to 11 gigahertz. But that type, 1200 watts again. The non-slotted type, intended for 18 gigahertz, also 1200. And finally, the DIN 716 connector works up to 8 gigahertz, rated for 2000 watts. So finally, a bit about the power and the comments thereon. If you look at the interface diagram for a BNC, you can see the pin contact. The maximum contact is 3.5 by 1.35 millimeters. Remember how tiny is the area through which the current is flowing, with skin depths of a few microns. And the circumference is 4.25 millimeters. Contact area is 15 millimeters squared. But in my opinion, that doesn't matter very much because, owing to the skin effect, you just go a little bit along the pin and then into the outer. So the actual area isn't what matters, it's the circumference of the pin that matters for power handling. The N connector has almost the same pin size. So that's why the power rating is the same. Its circumference is essentially the same. The DIN connector has a much bigger pin, and the circumference you see is 16 millimeters as opposed to 3 times as much. Therefore, it is much better at handling power, provided it's kept clean. But watch out in all connectors, if this pin is slightly in the wrong place, slightly displaced, you're going to have big problems. And John has kindly brought with him some examples, which I'll also hand round, of what happens if things get slightly displaced. These are all rendered by his own fair hand. So, this is my summary for connectors. Things to watch for. Am I in negative time yet? Almost. Oh, I am. Right. Well, we'll go through this very quickly. There is only a conclusion after this, so we won't be far off. Mil-spec N-type and BNC connectors have gold-plated inner contacts. That's what the spec says. Genuine gold plating does not look shiny. There is a wonderful metal that's been created that looks a bit like gold, but is shiny. It isn't gold, and it isn't satisfactory. Watch out for shiny plating. Silver-plated contacts are excellent. If you're going to plug them in and unplug them a large number of times, they won't do quite as well as gold, but they are a great low intermodulation interface. BNC connectors have relatively poor signal leakage because you can wiggle the BNC around. I would not recommend them for use above a gigahertz. Because coaxial connectors have become commodity items, there are so many available now, and some of them are so cheap and nasty. Even the major manufacturers have things in the catalogues called commercial. And what commercial means is made cheaply, and you think, oh, I am buying an Amphenol connector. Well, it's an Amphenol commercial range connector, and it is not as good as the mil-spec one. So if you're worried, if you have a critical application, have connectors manufactured to MIL-C 39012, and they will give you long life and reliable operation. And finally, when making up connectors, check that the pin is in the right place. If the captive pin connectors are best, but any connector you pick up when you've made it up, just use your thumb. If you take your thumb across the connector, you should just catch the pin on the back of your thumbnail. If you don't, it's in the wrong place. If it's sticking out a lot, it's wrong. If your nail can just go over it, it's too far back, and it will do what some of John's connectors have demonstrated. So to conclude, we certainly need feeder losses less than a couple of dBs. You're likely to need masthead preamps at 1.3 gigahertz. Best cables have solid outers and polythene foam dielectrics. Short feeders use foam dielectric types, and there are some very good ones now available. If you want defined specifications, you need M17/something types. Beware of fakes. Braided coax doesn't live forever, and avoid cheap coaxial connectors. The shinier they are, usually the worse they are. Thank you very much.
Thank you very much.
And could I have my samples back, please? Then I can reuse them for another talk.
As we've run on a little bit, I'm now going to curtail it and say, I'm sorry, there's no questions this time. Can we reconvene at 5 o'clock for the next talk?
Thank you. Break.
Thank you, Alwyn.
Sure.
Tour de force again. Thank you.